Let us now consider a more general Hamiltonian. That's case 2. More general Hamiltonian. In this case, we do not assume any particular form for this function h p x t, and let us take it arbitrary. Then how would you go from here to here? Since it's a configuration space path integral and this is a phase space path integral, of course we have to do the p integration in some way, and write everything in terms of an x integral and then compare. That's how we should do. Now, how do you do p integral for something which is arbitrary in p, where the p dependence is kept arbitrary? How could you do that? So it's like integrating a function, any arbitrary function. What you can do is to consider these as an arbitrary function of p, and then you can Taylor expand this entire function. It is not a function; it's actually a functional. Taylor expand the functional around the extremum. Then you have a power series in P which you could integrate. Right? That is the idea, but not for ordinary functions. But this idea to be implemented for functionals and path integrals. Okay, so this is what we will do now. So extremize this function px dot minus h px comma t. That means take partial derivative of px dot minus h p comma x comma t at p equals p0 is equal to 0. So then p0 is the value of p at which this function is extremized. And the first term, if you take the derivative, the first term is just x dot, and the second term is del h del p. Okay, so which means, so this means that x dot is equal to del p of h at p0. Now this of course is a function of then after you set p equals p0 this becomes a function. This right hand side is a function of p0 x and t, and the left hand side is x dot. This can be inverted to write p0 in terms of x dot and t. So let me push it a little bit. So this can be used to write p0 as a function of x dot and t. Right? So what we have done, we have extremized this function of arbitrary p, and we have found a functional form for p0 in terms of x dot t, which would extremize this. Now this is nothing but the nothing but 1/2 of Hamilton's equation of motion, right? So this is half of Hamilton's equation of motion. We'll come back to it later, just in a while. So therefore, this function p x dot minus h p comma x comma t can be written as p0 calculated at the extremum, p0 minus h p0 x comma t plus, right? We're Taylor expanding around that point. So this function evaluated at the extremum plus first derivative term will be 0. That is this condition. So if we can forget about that, then the sum n greater than or equal to 2. There is no n equal to 1 term. P minus p0 to the power n. Let us call kn x dot and t, where kn x dot t is 1 over factorial n. This is given by 1 over factorial n del n p px dot minus h pxt at p equals p0. That's what it is. You are taking higher derivative of the function with respect to p and then setting p equals p0. P equals p0 means this particular functional form. So then p is eliminated, right? P is eliminated, and that's supposed to be the case because it's Taylor expansion. The coefficients are independent of p. P dependence is in the power. So p gets eliminated in terms of x dot and t. So this is a function of x dot and t, which is why I have used annotation kn x dot and t. Now notice, what is this quantity? This is precisely the Lagrangian, because that is what you do while calculating Lagrangian from Hamiltonian. You do a Legendre transformation where you trade off p in terms of x dot, which is given by this. This is the definition of this is how p and x dot are related, right? So this is nothing but the Lagrangian. Therefore, the matrix element Fi is equal to dx dp exponential I by h bar integral dt I to f, and this entire thing can be written as Lx x dot t plus sum over n greater than or equal to 2 p minus p0 to the power n kn x dot and t. So of course the first term, this term, is entirely dependent on x, and therefore can be taken out as a prefactor, and that prefactor is therefore dx e to the power I by h bar sx. This is integral dtl is s, and the other factor, the rest of the factor does depend on p integral, and that's given by exponential I by h bar sum over n greater than or equal to 2 integral dt I to f p minus p0 to the power n kn x dot t. Now, what this means is this is p of t is a function minus p0 of p0 a function of xt, x dot t, and t, right? So written more explicitly, this is p of t over which the path integral is taken minus p0 xt, x dot t, and t. So for a fixed x, fixed path, this is a constant for the p integral. So let us define this quantity as a new variable, say qt. However, in doing what we want to do is that higher powers of p integration will be giving so let me first write it down and then explain. So let us define this as a new variable q of t, but not only q of t, but root h bar times q of t. What does that mean? What is the meaning of multiplying this by root h bar? So q is nothing but p minus p0. So what we are doing here is, we are doing a stationary phase approximation, or an expansion around stationary phase approximation of the functional dependence of this in the momentum. So we have extremized this in momentum direction. So this is a function that is supported over the phase space, yeah, as a functional. So phase space functional. And for the momentum, so there are two types of functions here involved in this. One is x of t, and x of t is a configuration space path, and p of t is a momentum space path. And now we have extremized along the momentum space paths, or have done a stationary phase expansion, in the sense that we have expanded the integrand from around a point where the momentum space integral has been extremized. Momentum space dependence of the function has been extremized. When you extremize them with respect to momentum only, what you get is a function, effectively a function of x dot and t, which is this. It is using this extremization, you are replacing momentum by a function of x dot and t. Okay, so for small h bar, whatever the interpretation is, that in classical mechanics, the Legendre transformation that we do for going from Hamiltonian to Lagrangian, it's a quantum extension of that, because at the leading order, h bar going to zero limit, only this extremum value is going to survive, which is this Lagrangian. But at subleading order, the higher order h bar contributions will be smaller. But how do you incorporate that into the equation? By scaling, by saying that p minus p0 is higher order in h bar. So the fluctuation p from p0, the fluctuation between fluctuation of p around p0, that is, if you write p equals p0 plus something, that is the fluctuation, that is that's a for any momentum function, how far it deviates from this classical expression, which is used while doing the Legendre transformation. Okay, so what about the functional form? What about the functional relation between momentum and x dot and t that you use while doing Legendre transformation in classical mechanics? That is interpreted as a classical value for p0, and any deviation from that is small, quantum mechanically small. That is how you are designing the computation. You are setting up an approximation method. Okay, so that deviation how do you tell that calculation that that deviation is quantum fluctuation around a classical configuration? Is by saying that the deviation scales by root h bar. If you do not keep this root h bar, then this deviation is order 1. You don't want that. You want to make sure that the deviation is quantum mechanical fluctuation. This is quantum mechanically small fluctuation when h bar is small. So this method, here you can always define a qt with root h bar. It's just a definition. You don't have to give a justification. But what it facilitates doing such a scaling, what it facilitates is the following: that doing such a scaling will lead to an expansion in powers of h bar, and that expansion is reliable when h bar is small. That is what you are doing, a perturbative expansion in h bar. Okay, so then this entire momentum integral, if you do this, is the entire momentum integral can be written in the following fashion. It's h bar to the power half integral dq exponential I over h bar sum over m greater than or equal to 2 h bar to the power m by 2 integral dt I to f q to the power m k m x x dot and t. Okay, so because dp, and because of the scaling, dp is root h bar times dq. So this is same as h bar to the power half integral dq exponential I. So when m is equal to 2, then it is h bar, that cancels this. So the first term is I times q square k2. Then the second term m equals 3, so that is h bar to the power half, so plus I times h bar to the power half q cube k3 and so on, where we have used a notation this means integral dt I to f. Now what are you going to do next is to take this h bar to the power half integral dq, then e to the power I q square k2, and then the rest exponential of the rest of the thing can be calculated in power series. Okay, and the result will be 1 plus h bar to the power half q to the power q cube k3 then h bar half q cube k3 square plus q to the power 4 k4 and so on. See, e to the power this quantity will have 1, and then the entire series will come down. That is the 1 plus h bar to the power half q cube k3 and higher order. But higher order in the sense the next one is h bar times q to the power 4 k4. But at this order h bar, the quadratic contribution from this term will come. which is q cube k3 to the power 2. Okay, right? So this is, if you call it x, so this is 1 plus x square. So this is 1 plus x. In x has a h bar expansion. The first term is h bar to the power half. Then the next term is h bar times this. That is a part of x. But then this part of x is of the same order in x of the order of a term coming from x square. This contribution coming from x square, which is h bar times half times q cube k3 square. Okay. Now you can argue using this calculation. Going ahead, you can argue that any order h bar odd half integer will be an odd power of q. You see, it is h bar to the power half. It says q cube. This is h bar, so this has even powers of q. But you can give a general argument, argue that at order h bar to the power odd integer by 2 should give you odd power of q. Now, if you have an odd power of q, there's an integral here. This is even power of q. So this integral is symmetric. Q goes negative and positive side in symmetric fashion, right? So if you have an odd power of q, then you can replace q by minus q, and it will just multiply the entire result by -1, which means it must be 0. So integral will vanish. So this gives you this type of integral vanishes. Okay, therefore only integer power of h bar will remain in the expansion. Therefore, the general structure of the result can be written in the following way. It is given by integral dx some m x x dot and t times e to the power I by h bar s of x, where m x x dot t is equal to m0 plus h bar m1 plus h bar square m2 and so on. So what I am basically doing is that all these h bar to the power odd integer by 2 terms, they will all drop out of this expansion because the integral will give you 0, and the rest is an integral of dq times this phase times some powers of q, in the path integral, and you will do the integration. The q will be eliminated, and the factors k3 k4, they are all dependent on x dot and t, and after performing the q integral, it will be a function of x dot and t with a integer power of h bar. And you can collect all these results at order h bar square, etc. The general structure is that every order of h bar will be multiplied. At every order of h bar, the contribution is some function of x dot and t. And remember that this entire calculation is sitting inside that x integral. Okay, so therefore there is an expansion in all powers of h bar, integer powers of h bar, where the coefficient is a function of x dot, local function of x dot and t. So that is the form of this result. So therefore the conclusion is that, so the conclusion here that that this, if I can be viewed as integral, a configuration space path integral I by h bar s with a suitable suitable definition of measure. And which means you can, if you absorb this function into the measure and define a new measure, I mean, okay, so this integral, okay, so let me not write it that way, and maybe I should better to write it in rate m explicitly. So m is a measure factor. Right? You have seen this example. For example, if you do a volume integral in Cartesian system, then in 3 dimension it is tx dy dz. But the same volume integral in r theta phi system is r square sine theta dr d theta d phi. So, so the coordinate element is not same as the volume element. So here you have a particular predefined coordinate element, but that is not the entire measure. The entire measure has an additional factor. Just like in spherical polar coordinate, we have r square sine theta as a measure factor sitting with multiplying the coordinate element dr d theta d phi. That gives you the volume element. Here you can view this as a measure factor, right? So what we learn here that if you wanted to look at it as a expansion around stationary phase approximation, if you view it that way, so if viewed as an expansion, I mean, now I'm talking about expansion stationary phase approximation in configuration space path integral. I mean, I've already done that for the momentum space. That is how I organize the momentum space integral calculation. Now, if you look at these expression, and then you can again think of a stationary phase approximation and think of a quantum calculating quantum fluctuation around the classical result. The stationary phase approximation by itself will give you some will give you the classical paths, but then you can have set up an expansion around that, which are the quantum corrections. So if you view the calculation in that fashion, of course, that is true only when h bar is small, and that is how we have set up the calculation to begin with. So we are committed to consider h bar to be a small parameter and interpret the result as an expansion in h bar. It's called semi-classical expansion. So viewed as an if viewed as an expansion around stationary phase approximation, and this is basically an extended lengthy way of saying lengthy way of what people usually refers to as semi-classical expansion. So if I refer to semi-classical expansion, it means this is what has been done. It has been expanded around the stationary phase approximation. Then the semi-classical expansion has a classical contribution in the leading order and then quantum corrections, right? That is how the entire calculation goes. And then if you view it as a semi-classical expansion, then there are two types of there are two sources of quantum corrections. One is optional paths. Yeah, optional paths means when you do a stationary phase approximation, as I explained earlier, the classical path x lower bar will this in the leading order, only that contribution will survive, and m will also be calculated only for classical paths like x lower bar, because m is a function of x dot t. So for the leading order contribution will be classical path, this phase calculated for a classical path x lower bar, and m calculated for x lower bar. That will be the leading order contribution. But then if you expand the action, just like in the momentum space, you can expand that action in the configuration space around x bar and define a new variable, say x root h bar times x minus x bar, and do the similar calculation and set up a further and that will give you a further h bar expansion. One h bar expansion is already sitting within m, which came from the stationary phase approximation in momentum space. So one source of quantum corrections are these optional paths in configuration space. So basically, two sources of corrections. So optional paths in configuration space, and the other is local modification of measure. Basically, since you are doing a stationary phase approximation in both momentum and position space, there are two expansions, there are two sources of h bar expansion. One coming from the off-shell paths in the momentum space, which means the off-shell expression between the relation between the momentum and x dot, whose classical value is given by this p0, right? So it is because of those off-shell functional form for the momentum in the dependence of x dot and t. That is one source of quantum correction. And in the position space, in the configuration space, there are off-shell paths which are away from classical paths. That is another. The nature of the mathematical origin of the both are similar, because I'm going to do, when I do a stationary phase approximation of this quantity, I will again do the expansion in the same way like this. I will do it here, x minus x lower bar multiplied by root h bar. Okay, so and therefore it will bring down another, say, m times n, where n has this integration results of that x minus x lower bar integrations, and they are also they will also give a h bar expansion. So those I'm calling as off-shell paths in configuration space. And already what I got here, which I'm interpreting as a modification, local modification of the measure, that already has an h bar expansion. So that is the another source. Okay, so this is the general structure. If you want if you start out with an Hamiltonian, then the Schrodinger theory, then the configuration space path integral will take this general form, and fundamentally speaking, you don't come up with a proposal of what this is going to be. It all depends on how you define the theory. If you have defined the theory by giving a Hamiltonian, this hp x p comma x comma t, that is what defines your theory, then you have to figure out what the path integral statement is, using the usual Schrodinger language, I mean method. Okay, so